Okay, good morning. So today I want to get, I want to get as much done as possible for chapter 6. We have resonant frequency, Bode plots, and then I want to go over the example problem that I rushed through last class. So I'm going to go over that in detail. There's one thing that is the, not one thing, that's the end of the slides. Let's see. And I want to do that because that's a question in the homework that is due tomorrow. Okay.
Professor, I had a question.
Yes.
I guess how are we supposed to add impedances in parallel if one of them is real, one of them is, I guess, imaginary?
Is this about the quiz?
Yeah.
Let's talk offline, please.
Okay.
Meaning like office hours or after class, if you don't mind. Yeah. So let's see. Okay, so this is one of the questions on the homework. It regards to Bode plots. And again, we will go over this topic of Bode plots in detail, but this is one slide, one thing that I wanted to mention. So Bode plots was developed by a engineer working for Bell Labs around the 1930s, mid 1930s, I believe. His name was H.W. Bode, the Dutch engineer working for Bell Labs here in the U.S. And he was tasked with determining the frequency response of various circuits that were in use at the time. And so he came up with this graphical description where you could do an approximation, especially for like filter circuits, and you could plot a large range of values using straight line approximations. Okay, so these plots came to be named after him. Bode plots, they were a very invaluable tool when you have to do graphical solutions manually. Okay. So this right here shows you a Bode plot of a low pass filter. Low pass filter. Okay. Now, typical low pass filters would have a frequency response that looks like this, right? This is the pass band, and this is the block. These are the frequencies, and this is your output on the y-axis. Lower frequencies are passed, higher frequencies are blocked. So Bode plots are basically comprised of asymptotes. Asymptotes, as you may or may not know from geometry, is a tangent that approximates or approaches zero for a curve as the coordinates of either one tends towards infinity. So it's a straight line approximation for a curve, okay, simply stated. So basically here, if we say this is the pass band, these are the low frequencies, these are the high frequencies, right? And this is your break frequency FB. So if it's a low pass filter, low frequencies lower than FB are passed, frequencies higher than FB are blocked. So the asymptote that describes the low frequencies is known as the low frequency asymptote, which is what we see here, right? And the frequencies, the high frequencies are described by the high frequency asymptote. Okay, so for a low pass filter, the high frequency asymptote is basically a straight flat line, right? It's a straight flat line. Sorry, low frequency asymptote is a straight flat line. And the high frequency asymptote approximates the slope of that curve, again, as a straight line. So it's a straight line that goes like this. And so it's just two lines. You can describe the functioning of a low pass filter or any kind of filter system, basically. So you have the low frequency asymptote here. It's pointed out. And this is the high frequency asymptote. Okay. And these slopes for a first order filter are always standard. It'll always be 20 dB per decade. The key figure is 20. And we will look into detail what a dB and a decade means. Okay. dB and decade are terms that we use to compress our scales. So we can describe a large range of values into a small chart. So for a first order filter, that slope is always 20. For a second order filter, that slope is 40. Third order is 60, and so on and so forth. So the sharper the slope, the better the performance of your filter. All right, let's take a pause. Let me know if you have any questions. Any questions? Okay. So what would it look like for a high pass filter? So if this is our FB here, low frequencies, high frequencies. For a high pass filter, high frequencies are allowed to pass through. So the high frequency asymptote should be a flat line. So it should be something like this. And then low frequencies are blocked. So low frequency asymptote would have a climbing slope or an increasing slope, right? Something like this. Okay. Low frequency asymptote, high frequency asymptote. So this would be a very easy and efficient, not easy, but an efficient way of describing the system, like a filter response of a system. So this is one of the questions on the homework problem. Several students have already begun the homework that is due tomorrow, because most of the material is covered. One of the topics is the problem. And so the next thing I'm going to do is cover that problem. Any questions before I move on regarding filters? Okay. All right. Let's see. Okay. So early on in this chapter, we looked at a problem where the transfer function of a system was described to us graphically. The magnitude and phase plots were given to us. An input signal was given to us, and we were asked to determine the output voltage, right? V in of t was given, V out of t was the deliverable. So we took a look at the transfer function. We calculated the break frequencies and the input frequencies of the three components of the input signal. Then we determined the transfer function at each one of those frequencies and determined our output. So the approach is similar for this problem. We are given a circuit. Now, obviously, we know what kind of circuit this is, but if we didn't, then we would perform the analysis using our table, and we would determine what kind of filter it is first. Okay. We studied 4 filters so far: RC, RL, and high pass and low pass using both RC and RL. Okay. And essentially, again, as a reminder, the circuit's the same. You have a RC circuit. If you take the output across the capacitor, it's a low pass filter. If you take the output across a resistor, you're obtaining the high pass components. Okay, and RL is the exact opposite. So by observation, we know what it is, but if it is a new circuit and we don't know, then we perform our analysis using our table. And frequency tends towards 0. Capacitor behaves like an open circuit. So we model the circuit and we determine that V out would be equal to V in. at low frequencies. When F tends towards infinity, capacitor behaves like a short circuit. Output goes to 0. So for high frequencies, output is 0. Low frequencies, output is equal to V in. So it's a low pass filter. Once we determine what kind of filter it is, we look up the standard equations for a first order low pass filter. A first order low pass filter has a standard equation that is given by H of F is 1 over 1 plus JF over FB. That's the standard equation. We simply take that equation. That's for the magnitude, sorry, not magnitude. That's for the transfer function H of F. If you wish to find just magnitude, then there are other equations that we can develop from these. That's already there in the slides. But again, H of F is a complex quantity. So once we determine H of F, we can easily obtain the magnitude and the phase from the final answer. Okay, so H of F is 1 over 1 plus JF over FB. FB is a constant given by 1 over 2 pi RC. R and C values are given to us. 10 microfarads and 159.2 ohms. We plug in the values for FB, sorry, R and C, and we determine the value for FB. So far, so good. Okay. Then we need to look at our input and determine the frequencies for all three components. So in this case, as I stated last time, when we first write out the phasors for all three input components, we see that the phasors are all the exact same value. Magnitude of 5 with a phase angle of 0 degrees. The only difference is in the frequency or omega. Otherwise, they're all the exact same components. But because the frequencies are different, we cannot add them. You have to handle them as separate components. Okay. In a DC system, if you have multiple sources, you have 2 or more voltage sources or 2 or more current sources, if they're connected in any way, it is possible to reduce them. In AC, you can only do so if the frequencies are the same, chapter 5. Okay, so here the frequencies are different, similar to example 1 that we did early in this chapter. We treat each individual component separately. We see that the frequencies are 10, 100, and 1000 hertz. Standard equation, omega is 2 pi f. So we equate 20 pi, 200 pi, and 2000 pi with 2 pi f, and we obtain F1, F2, and F3. Right, let's take a pause. Think over the steps so far. Let me know if you have any questions. Any questions at all? The steps make sense. There is a problem in the homework that you would have to solve with these exact same steps. Yes. The V in of t, yeah, that is given to us. So the problems, yes. So V in of t is given, in the circuit diagram is given, and we simply asked to find V out of t. Any other questions? Okay. So then we take the standard equation for transfer function and we plug in the different values for F1, F2, and F3. So for the first one, you have F1 over FB. That gives you 10 over 100. Then you have F2 over FB. That means the second component has a frequency that is exactly equal to FB. That is the midway point. and F3 over FB. Thousand over 100. Have you all tried to do, solve these equations in your own calculators? Have you obtained the same values? Anyone? So 1 for h of 10, meaning at frequency F1, you get 1 over 1 plus j.1. You can directly program this equation into your calculators, and you should be able to obtain the values that are shown on the board. If you're solving this manually, then what I would do is I would convert 1 plus j.1 into polar form at a magnitude and at a phase angle. I would have magnitude and phase angle. That's how I solved it. Okay. So there are multiple steps to go through. So this would be magnitude M, phase angle theta. And that's how I solved it. But again, if you have a programmable calculator, you can program it directly. Yes. Yes. So the question being asked is, if I solve this manually, then what do I do about the numerator? The numerator will simply become magnitude of 1 and phase angle 0 degrees. And then, of course, magnitude gets divided and phase angles get subtracted. Then I would have an answer with a magnitude and phase angle. I would convert it back into either rectangular or polar if I needed to. But once you solve this, you obtain h of 10. You obtain h of 100 and h of 1000 values. Okay. No matter what kind of filter it is, if your input signal has a frequency that is equal to the break frequency, your magnitude will always be 0.707 and your phase will always be minus 45. Okay, your phase will always be minus 45 and your magnitude will always be 0.707. That is the point, that is the transition point between the two. That is the border line between the pass and the block. Okay, pass band and the block band. So that's the point where the voltage, the output voltage, drops to 70% of the input voltage. You remember, it's 0.707 times V in. So it drops to 0.707 times. Then, once you have h of f, simply take V out or V in, multiply with the respective values, and you obtain your answer. Okay. Final answer is asked in the time domain. So your answer should be V out of t. Final answer is inverse phasor transform, and you obtain V out of t. Yes. A ideal filter, of course, would have a response that looks like this, straight down, right? Anything to the left should be allowed to pass through without any signal loss, meaning if it's a 5-volt signal, all 5 volts should appear at the output, and anything to the right should have a value of 0. But real-life filters don't work that way. So the demarcation line is where we drop our power to 50%. Power, in case you forgot from chapter 1, is V squared over R. So when voltage drops to 70%, 0.707, power drops to 50%. That is the point where if you have a filter circuit, remember, filter's job is to block an incoming signal, right? But if it's right at the break frequency, it's not going to go all the way to 0. Incoming signal, break frequency, instead of going all the way to 0, it's only going to go to 50%, meaning the incoming signal is dropped to 50%. So we design our systems keeping all of those facts in mind. So even though we do obtain 50% output at the break frequency, we consider it to be blocked. Okay, so even at 1000 hertz, if you look at the circuit right here, at 1000 hertz, we still obtain 0.5 volts. So 1000 hertz signal coming in, a low pass filter is supposed to block it completely, but in real life, it cannot block it 100%. So you still get half a volt. That half a volt signal is then ignored. Okay, we design our circuits to account for that fact. So it's still, even though it's passing, we say it's working as a low pass filter. Does that make sense to everyone? All right, let's take a pause. Let me know if you have any questions. Oh, so one point I was making was the break frequency, FB, is also known as the half power frequency, because that's the frequency where the power drops to 50%. So at FB, V out is 0.707 times V in, but P out power is 0.5 times P in, the input power. Okay. So now let's take a pause and then let me know if you have any questions. Any questions at all? No. Okay. All right, shall we move on? I'll introduce the topic of resonant circuits then. These are equations, standard equations for magnitude and phase. Just there for quick and easy access. But again, you can look them up later. Okay, so resonant circuits, series resonance, and then we also have parallel resonance. These occur when you have two opposing energy storage devices in your circuit, like an inductor and capacitor. Inductors and capacitor are duals and mirrors of each other, right? Impedance for inductor is plus 90, impedance for capacitor is minus 90. What that means is when you apply an AC signal, in the positive half cycle, energy flows into the inductor, and in the negative half cycle, the energy flows out of the inductor. For a capacitor, is the exact opposite. For a capacitor, energy flows into the capacitor during the negative half cycle, and it flows out in the positive half cycle. Completely opposite. So when you first flip on the switch and you apply power to a circuit containing R, L, and C, positive half cycle energy flows in the inductor, negative half cycle it flows out, but negative half cycle energy flows into the capacitor. And so it bounces back and forth between the two. At one particular frequency, depending on the values of the inductor and capacitor, there could be voltages and currents that are larger than the input voltage that could appear in the circuit. Okay. Those of you who are taking the lab, you might have noticed when you performed lab 6, when you did an RLC circuit, the voltage across the inductor was larger than the source voltage. The reason is the source is sending some energy to the inductor, but the inductor also receives stored energy from the capacitor. And so for that reason, that voltage may appear larger than the source, okay? Just in magnitude, again, because capacitor impedance points straight down. This is a very important concept for the last topic of 201, which is AC power. AC power is all about energy transfer between inductors and capacitors. This is a very important concept for there too. Just one point I want to make, we are almost out of time, is that at resonant frequency, you have a bunch of frequencies coming into a system. If you have a RLC circuit and you have a bunch of frequencies coming in, at one particular frequency, the magnitudes of the inductor and the capacitor are exactly the same. But the phase is opposite. So at resonance, magnitude of ZL is equal to magnitude of ZC. However, the phase is exactly 180 degrees opposite. I don't think that's the right mathematical representation, but I'm going to run with it. 180 degrees out of phase. And so they cancel each other out. Okay. And the only thing that's left in the circuit is the pure resistor. So we'll end class here today, and I will pick up here again on Wednesday. All right. If you have any questions, I'm happy to answer them. So there was a question earlier about, let's see, adding or subtracting real and imaginary. Let's see, student.